Well, thank you all for coming. I feel super humble. Yeah, so probably, to be clear, I have 0 slide. I'd like it for it to be an exchange, but before that, hopefully I will talk to you about why we built ZML the way we did, why was the first thesis, and how it went, the problems we encountered, etc. But please, feel free to interrupt me. I, really would like to, if you have questions, to answer them, and we'd love for this to be a conversation. So the first, problem that, like, the fundamental, problem that I wanted from a technical perspective. Also, mind you, I've been doing a lot of, meetings, so I'll try and be more technical. But if I'm too technical, please, pull me back. We can go wherever, but I would assume you guys want a bit of technicality. So the idea was to essentially build, at the very bottom, build the framework, the AI framework that I wanted to use as, next operator of a pretty big, I would say, infrastructure. In terms of size, we had about 14 million requests per second. We were the second spender on Google Cloud in Europe for like 3 years with a discount, right? So that's counting the discount, 80%. We had a few good shots, and ultimately, when it came time for me, so not at that company, but after that company was killed by Snap, and I will go on record. Essentially, I decided to, prod an AI model. Didn't really, found what I was what I wanted in terms of the tools, the observability, the robustness, etc. And it felt really duct taped. And the first, I would say, 2 problems I encountered was that either I would essentially pay money to OpenAI, or I would pay money to NVIDIA. And there was nothing, fundamental, from my opinion, that would justify that. There were a lot of circumstantial reasons, but not really fundamental reasons. There were other chips. There were, Llama just came out, so that was a 1.5 years ago, but Llama just came out. So essentially, eventually, I set out to build the framework I would have wanted to use, and ultimately also the products I would want to use to run these models. So the first thing that I essentially did that I essentially didn't find on the market was pick a side between inference and training. You could think of them as one being research, the other being production. They have very different incentives, and everything I would find essentially was trying to do both, but ultimately it was just training bent, a bit to do inference. So there wasn't the right tools, there wasn't the right, philosophy. Everything was made for fast iteration, but not for robust, production and high performance, and where everything matters. So the first thing I did was essentially, well, inference is a universal problem. No matter how sophisticated you are in that field, you will touch it one way or another if you decide to do AI. And not only LLMs, mind you, all of AI. And if you actually pick a side, there's a lot of things that change in the way you do things. What you want, ultimately, is using, if you can, I used to, operate a Python production for 10 years. I have the scars to show for it. I'm sure, some of you have too. I love Python, but yeah, too many sleepless nights. But yeah, I wanted to have a language that I could integrate into anything that was fast, that was typed, that was compiled. And also, I wanted my models to be also compiled, and I wanted them to be compiled onto any chip. It didn't really matter whether it was NVIDIA, whether it was AMD, whether it was CPU, whether it was whatever new chip, AWS, and so on. And picking a side, essentially allowed me to do away with the bad abstractions. What felt for me, at least, bad abstractions. So, for instance, one thing you do not want is what's called eager execution, meaning that every operation runs after the other sequentially. You want a compile model. You want operator fusion. You want kernel generation and so on. There's all. So. Oh, there we go. And also, I wanted it to be zero compromise. If I would, change, from, let's say, AMD to NVIDIA, or vice versa, rather, I didn't want it to have a first-class experience and a second-class experience. So the cost of change had to be, not cheap, but actually zero, without compromise. And the last thing I wanted to do was to solve all the little things, the little pains you get on the way to success, right? From the cross-compiling, to the packaging, to the trimming, to all of these little, fire ants that bite you and ultimately win, right? So this is what, I set out to build. So that was a year ago, mind you. And now a year later, we've done it. So we just open source, the framework. And I guess the number one question we get asked is, why Zig? And actually, so at the very beginning, the answer was, so from a technical perspective, there were not that many languages we could have used. It could have been C++, or it could have been Rust. The reason being that integration was a big factor at play. We wanted it to be integratable, because it's not about essentially floats over a socket. So if you want, let's say you're doing like image processing, you cannot send bitmap over the network. It's too ineffective. So it has to be, integrated, and also without, I would say, compromise. So that ruled out Go because it's a scheduler, etc. We didn't go with C++ because it's C++ and it's a tough sell, in an ecosystem that does Python. Rust would have, so it would have worked, right? We could have, from a technical perspective, everything would have worked. But at least from, I would say, product perspective, C++ didn't make sense, and Rust, the onboarding was way too high. Essentially, there was a big ask for the people in that community to say, hey, you're going to fight the borrow checker on your way to your deployment. So this is, I'm trolling a bit, but not that much. And enter Zig at that time, which essentially got critical mass. So that was the escape hatch. We had the Go-like syntax, a Go-like syntax that is nicer to use than C, very high performance, and also there's this thing called comp time, which essentially allows us to write what feels very high-level code, but it turns out compiles to very low-level, very optimized code. Some may say that there was a discussion on Twitter recently that it doesn't really matter because most of the time is spent on the GPU anyways, so Python is here to do the glue. I don't find that argument to be very true because on model deployment, you don't have only the model code. You have the integration code, so getting the data from outside. You have the normalizing code and the model code. And you have to be fast at essentially ingesting data, normalizing data, running it through the model, and out. So these little things add up, right? And they add up very quickly in production, of course. So this is what we set out to build. Thankfully, Zig had achieved critical mass last year thanks to the release of Bun. So that was all the signal I needed, and so we went with it. On the journey, we found so many great things about the language, but ultimately, we're very happy about the things we could have done. We are doing, especially on the model code, thanks to the language. The last piece of the puzzle was how to essentially glue all this together. From, I would say, the little things as in, I'm on my Mac, how do I generate, let's say, a Docker image for my, Intel Linux, with CUDA inside and so on. So all these little things that creep up, essentially. And this is, why we went of the build system of the whole thing to be Bazel. So this is how we do the runtime sandboxing. This is how we achieve the zero, I would say, $0 code chip change, if you will. And so we're very happy with our choices. And I guess probably the last part is achieving essentially zero compromise performance on chips. So we'll go a bit technical on that, but the idea is that The way you achieve that is by essentially finding the right balance between expressibility, whatever, I don't know what you say, and interpretation. So what I mean by that is that you want to have a way to talk to these chips that is low level enough for you to express what you want, but high level enough for the compiler or the chip, whatever it is, to essentially do the optimization, do what they do best. So that was the whole case behind the creation of a framework called MLIR, which doesn't stand for machine learning, it stands for multi-level IR. MLIR is essentially a bytecode manipulation framework. The important thing is that you have dialects, which essentially express semantic operations, and you have transformation between these dialects. So you can go lower, you can go higher. It's very loose, right? So some win, some lose. And for that, we use that essentially the way to emit IR to the chips, and the dialect we chose was the one that was used by Google to run their TPUs. So it was battle tested in terms of, because semantics is, in this case, is all that matters. If you have the wrong semantics, you don't get the performance, you get the degradation, you get abstraction leakage, you get all these things. So the semantics are really the core of the programmability of this. And it turns out that in 2022, all the vendors rallied behind Google, well, not behind, but with Google, to essentially around the consortium that's called OpenXLA, which has lots of things, but one of them is the interface to a standardized interface to a compiler and a standard dialect to talk to this compiler. So this is what we use, at the lower level to emit IR for the chip, talk to a compiler, sandbox it, sandbox the runtime, cross-compile it, package it, and then finally run it. And in the near future, serve it too. So that's roughly the gist of the whole thing. So now it's not working. It's open source. You can just go and download it and try it for yourself. I have a few demos, of course. But mind you, right now it's a framework. You have to write the code in Zig too. So we did that by choice. We have tools internally to facilitate the imports of PyTorch or whatever it is, or Onyx and so on. But we just want the people who are actually crazy enough to dive in. We do think that at least in the medium term, it's a lot cheaper to actually write the model in Zig, or in ZML rather, because we're talking like 200 lines of code. Because it's actually a lot shorter than writing in PyTorch. There's less, raw lines. There are about half of the lines to write ZML code than PyTorch code. So it's a lot clearer. There's much less maintenance. And so, yeah, a few people have already announced they would do it in prod.
Sorry, can you explain a little more why it would be shorter in ZML than in PyTorch? PyTorch is in Python, so you would assume that it's high level enough that it's
right.
shorter.
Yeah, so there's a few reasons for that. One is PyTorch models are essentially executables, and they're written like executable. So you have very little visibility about how the model is organized. I mean, you could do it the right way, but a lot of people don't. So it literally reads like operations in line. This is the first thing. The second thing is ZML code is organized by modules. So you see, so let's take, let me show you, it might be easier. Let's take mnist, right? So if you look at mnist code, this is the model. This is basic, digit recognition model. For those familiar, it's a very small model. But the way that model you see is so there's the bigger model, mnist, and then it's you have two layers that are essentially submodules. And so we actually exploded it so that it reads very verbose. And so this is the code you write roughly. So you essentially say, this is my fork function, and I want to compile that, or I want to compile that module and its submodules. You get an executable back and you run it. Now, the reason it's smaller has a lot to do with the IR itself. So, and also Zig. we have this thing called axis tagging, and the idea is that you give semantics to axes in the tensor. So say, for instance, you have an image. You wouldn't have, axis dimension 0, 1, 2. Let's say, 8 width channel. You would have, you would say, well, my image is like .h, .w, .c. And if you do transformation on the tensor, that tag is following. It's like name tensors in PyTorch. Only we actually bend a bit the Z compiler to enable it as a native without strings, essentially. So, in that case, you could say something like, input, with tags, and then you can give it, I don't know, let's say 2 tags, right? Let's say in the example I said, .b, .c. Now, I can do input, .dim, .h, right? And no matter if I do transpose, if I do whatever, that .h will follow. So it's kind of nice, but a lot of the code when you write a model has to do essentially with putting tensors into the right, I would say, expected shapes and expected, format that the operation will run. So what you find is that the operations you're going to do, so let's say matrix multiplication, is actually pushing on you semantics. So, and you actually do a lot of work to adhere to these semantics. Because that IR was essentially battle tested and rallied by all the hardware community, there's no implicitness. So there's no, for instance, matmule. That matmule you see is an emulated one. We have dot. And so the way it works is that semantic that used to be implicit by the operation is now pushed at the tag level. So what essentially that creates is that you completely remove all that bookkeeping code. The reshape, the transpose, and so on, because you essentially said, hey, this is how I want my operation to run, given these, axes. And some operations actually will push you, axes, tags, too. So for instance, if we look at SDPA, the real meat is here. This is a very naive SDPA implementation, right? But this is it. And what you see is that we, multiply, dot product, Q with K, and we contract on the HD dimension. So there used to be a lot of, transpose and, whatever, 0, 1, 1, 2, 0, and so on. It's all gone because we just tell it how to do the operation. So in short, there's a lot of code that just instantly disappears because of that. And the last thing is, because we propagate that to the IR level, not only it's shorter, but it's more performant, because there's a lot of operations that just don't have to exist anymore.
Sorry, I'm going to give you a mic to record questions. So if you ask a question, you can speak into the mic.
Should I press any buttons or
no,
just?
Okay.
So I'm just curious, when you say performant, did you actually did some comparison, like neck to neck with the PyTorch implementation NIST? And
we don't put out numbers because it's very easy to get shut down from the sky if you make a tiny claim or whatever. So I can give you the numbers offline, I would say, but for now we don't put out numbers. But it's more performant because in PyTorch you execute operations one by one. So if you do the famous case is transpose, which is a null operation. So if you run eager, you will transpose, materialize, do another transpose, materialize. And you have to copy, you have to do all these things. So this is an operation you can remove completely, right? So what a lot of people do essentially is they show they describe the graph and try and do these optimization at the graph level, and only materialize essentially when you pull the data. But this is the job of a compiler. Right? So this is why ultimately it goes to the cool thing is that it goes to MLIR. Through MLIR, it goes to the chips compiler, which then runs its own optimizations that are very specific depending on the chip and so on. The good thing also is that because of MLIR, there's a varying level of abstraction. So for instance, we could say to the chip, hey, I just want to run attention and not, a dot product, right? Well, actually 2 dot products and add in a softmax. And we're able to do this and push that at the compiler layer thanks to the IR. So it is quite a bit, we haven't spent much time on performance, mind you. Right? You look at that implementation would, probably have a few people faint in the ML community because it's very naive. But it works really well because of all the little things, that essentially happened before.
Yeah, please press the mic.
What do you see the relationship between ZML and other industry initiatives like Triton Lang?
Like what?
Triton Lang.
Oh, so Triton is very cool, but there's a pretty big problem we see with Triton. So for those who don't know, Triton is a way to essentially program NVIDIA chips without doing CUDA, without doing C++. It's pretty cool. The main issue with Triton is that it's very cool, as I say, as a compiler tool, but if you use it as a library, what happened, which is actually the scenario that happened with the H100, is that you don't write code for CUDA, you write code for the chip. So you get nice performance, it's very easy, it's Python, etc. But now, then H100 comes out and the performance is terrible and everybody, is freaking out, which was the December 2023 scenario. Now, mind you, on the CUDA side of the compiler infrastructure we use, which is called XLA, there is some Triton. You can use Triton. So it will generate these big kernels. I mean, it works. It works pretty well, but what works also really well is cuDNN. So cuDNN. So essentially, there's 2 ways to look at the problem. Either you generate big kernels that do the forward pass. In our case, it's like, for each layer, there's a kernel, roughly, in the case of Llama or a transformer. What we found is that there's actually a slight performance penalty as opposed to just using the raw, cuDNN or Rock Blast kernels. For instance, in the case of AMD, there's 100 times, performance penalty of using Triton because there's a lot of missing things here and there. But if you switch, to Rock Blast kernels, it works really well because it runs really well because you encode the whole graph into essentially the GPU pipeline. So there's no overhead in launching kernels. They just link between themselves. And we actually see that in profiles. There's like 0 time between kernels. And also in the case of Triton, sometimes also it's not a silver bullet if you have synchronization points. So if you do like this big kernels, it's sometimes not easy by hand. It's sometimes not easy also to do it very parallel, and you see sometimes a lot of sync threads, which actually kill performance.
I had a question, but no, I actually have 2 questions. My first question is pretty basic, but how would I test this? Is there an established way to test my model? Is it easy, and is it a strong suit of ZML, or is it like in the average?
So it's actually a lot easier, but not from where you would expect. So this is an example. Actually, let me load you MNIST is good as any. So this is the model. So MatMule, whatever. But it's not only about that. It's about how do you load the weights, how do you compile, and all of these things you have to do essentially before the model is run, right? You talk to the accelerator, what is the runtime of the accelerator, how do you deploy it, et cetera, et cetera. So from a model perspective, it's pretty simple, right? But by the way, mind you, in all languages. if you look at Python and PyTorch, yes, it's 3 lines, but there's like half a day of setting it up for it to finally load. So in our case, there's not. So this is like a small MNIST, so this is essentially UI code. The important part is that here, we open, so we have a torch loader that is entirely written in Zig, no Python. So we open the PyTorch checkpoint, then we populate the shapes. So the idea is that when you compile, you do not want, or at least in production, you do not want, I would say, invisible JITs. You want to be sure, when is, the time you compile the kernels, well, the programs, and when is the time you actually run them. So what you do is like, you open the model, you load the shapes, then you compile the model, and as the model is compiling, you actually transfer the weight on the GPU, on the accelerator. Once that's done, so this is, what you see here. Then, you wait on the compiling, and then what you get at the end is an executable, which you just call. So this is what happens here. So here I'm just reading, the sample data. So sample digits, this is a digit recognition. I just read them and then read them into a tensor. So from the CPU memory to the accelerator memory, so that you recognize, the shape of the tensor, the data type of the tensor, and then I just call the executable. I get a result back, which is this one, and out to the races. Now, this is only a short part of the story. So the model code, the weights, loading code, the compiling code, but then there's also, runtime, right? And so this is actually a demo I had for you guys. So the idea is that it's not only about, is it working? It is. It's not only about, just having, the model, having it compiled. Then it's about how do I run it on NVIDIA, and how do I make sure that it runs? My machine doesn't have, let's say, CUDA installed. This is the case of the machine on the left, which doesn't even have CUDA, only the drivers. And so what we'll do essentially, this is a, yes, actually let me kill it and I will come back to it. Can you guys see it? I can make it even bigger. So essentially what we say is, so this is all from source, mind you, right? So I pre-compiled so that you have to wait. So what I'm saying, I just want to run Llama 3.1 and I want to use the CUDA runtime. That's all you need to do. Everything is taken care of. And so what happens is we download CUDA, we repackage CUDA, we strip CUDA actually by 10 times. And then we make sure that the CUDA version you use, the cuDNN, whatever, is bound to your model. So there's no CUDA version mismatch and whatnot. That's all you need to do. You run it. And so it has found, actually let me, so that, well, you see it has found the devices, then it's compiling. So this is the IR. So this is, it had found 2 devices, the CPU device, and then the CUDA device. So it selected that one automatically. It has found 2 GPUs. Then, we load the model, etc., debug code. This is the IR we send to the GPU. And then this is the model executing. So what you see essentially is, we load the weights, we compile the model. This is the prompt. We can choose whatever. It's a llama, right? And there you go. Yeah. So I don't know what it's. There we go. So this is CUDA, right? So nothing fancy. It's CUDA. You guys know. So let's ramp things up and go on AMD chips. So again, pre-compiled because I want to have you guys waiting. Actually, you know what? Let me just copy that as is. and just change by ROCm. So this is AMD's runtime. And we run it. There's no ROCm in the machine. It found the GPU, it compiled, and now it's going to run the model. So there's literally zero code change. This is the same binary. I can also make an archive out of it, copy it over. Everything is sandboxed. There's no provisioning of any sort. The good thing, or at least to me the compelling thing, is that you can, like, what I'm showing you is like an example implementation, but ultimately the assembly to how to do that is all, you know, in the sources. You can say, all right, now how do I turn that into, you know, so here I'm running, but let's say, how do I turn that into an archive? So just the llama model without the weights. And this is an example of building an archive, a self-deployable archive that will, you know, that you can deploy wherever you want. You copy it, you run it, it works all of the time. And from that, you know, out of that archive, we can actually build a Docker layer. And out of that Docker layer, we can build Docker container, which we can push and cross-compile and everything. So that's it. ROCm is a bit heavy, so but there you go.
And that includes the model?
Not the weights, but the model, yes. Because the weights, you want to keep them separate. They're like 140 gigabytes, so you may not want to keep that into an archive, right? But the important part is that these little things, you know, they add up. For instance, you might have seen that we're compressing in GSTD instead of gzip. And this is how we turn, you know, 8 minutes of unpacking CUDA into 4 seconds. Because we use a different algorithm, because we strip, you know, the unnecessary weight, and so on and so forth. So we tweaked the compression a bit, so it will take a while. But you get the point. Yeah, yeah. Cold start, like cold start.
So this is what I send to a bunch of different machines in my cluster.
Yeah. Because the idea is, like, let's say you run in the cloud, you know, you want your auto-scaling to be pretty, you know, fast in case of the machine goes down or whatever. And if that number, you know, is like, let's say under a minute, then there's a few things you can do. First is like you have less overhead of, you know, over provisioning, but also if a machine goes out because it takes a minute for another one to come up, you don't care. So you actually can run them on spot instead of reserved, right, or on demand, because they're cheap to create. Whereas if you're provisioning, I mean, there's a number that comes out over and again is like tens of minutes, you know, 15, 20 minutes. It's like if it takes 15 minutes for a machine to come online, you know, you're not running on spot, right? Because if a machine goes out, it's terrible. And this is the same, you know, and of course, actually, let me, no. I'm on my Mac. Let's see. And I can run that same command. Where is it? Here. So I want to do, where are we? Here we are, and I want to say, actually this time I'm going to build with a TPU. And actually I'm going to create an image. So I'm running from, this is on my Mac, right? This is local, but this is actually going to download everything. It's actually compiling, cross-compiling to Linux. It download, in this case, the TPU runtime. It could have been CUDA, whatever, it doesn't matter. And at the end, what I'll get is a Docker image that is ready to deploy, the OCI and everything. Trimmed, you know, so in the case of CUDA, it's like 500 megabytes instead of like 6 gigabytes. It unpacks into 3 gigabytes instead of 26 gigabytes. So all of these things compound. But mind you, there's nothing I did. My machine is completely vanilla. There's nothing particular. It's completely isolated. And so this is ultimately the promise we do, is that it's not also about the model. It's about all the things that add up on that journey. And this is how we achieve true, you know, we feel true cross, you know, true agnosticity of the chip. The code, the runtime, the deployment. So hopefully it will go, it will do its thing. So that it's I did a build, but I didn't do a Linux build, so now it's doing one. Yes?
How would you stack rank
How would you stack rank the value propositions, deployability, portability, speed of inference? Like how would you stack rank as your design goals?
Optionality of the compute, being the first one. Reduction in engineering cost, because you go from like spending, at least a day to get something running to, well, you've seen it. So, I may go on a limb and say, productize and professionalize these tools, essentially. So it's a compounding thing, right? But what we're starting with is serving, because this is where, everybody, is hurting and everybody wants us. And also it's the one that is the easiest to abstract. Just build an OpenAI compatible server and off to the races you go. But it's going to be built on that. So we'll have the same, actually one thing I didn't do that I'll do after when it's compiled is that you don't have to choose, you can choose multiple. And the binary will run anyways. It will try and see, oh, I have a ROCm plugin, I'll try and load it. Oh, there's no ROCm GPU, I'll just go to another one. So all of these things will be available into the whole serving stack, right? But it starts with the tech, obviously. And of course, on top of that, then the serving, in general. Hopefully we'll finish.
What do you mean by the serving in general?
So, like, there's a pretty big gap between an ML framework and a serving, let's say an LLM serving server. So this is that gap, like observability, deployment, loading the weights from cold storage as opposed to loading from disk because it's cheaper, on-prem, orchestration, all of these things. But these are like things we used to deal with, back in engineers. They're not new. Like we're reusing. This is also a big part of, what we're after is like leveraging the 10 years of back-end engineering that went, and so yeah, this is the image. And now I could push it actually, maybe. Let's try. And now it will push when it's done. Oh yeah, so it's pushing. There we go. And so yeah, you go from essentially your code is to a fully self-deployable image that is trimmed, that unpacks very fast. In the case of CUDA, actually, you can try and download it. In the case of CUDA or ROCm, for instance, we can do a lot of more things, such as removing unnecessary bytecode. So you can, on top of it, over 40% more, size reduction. So there's a lot of knobs you can tweak. You don't have to tweak them all. They're same defaults. And all of this is from my MacBook Live.
I just wanted to make a comment. Mm-hmm. So, the only other Bay Area meetup we did on a programming language other than Python was Swift TensorFlow launch.
Right.
So the day we launched it with Google MLIR team, Sundar Pichai tweeted 5 hours before, we're giving MLIR to LLVM Foundation.
Wow.
So they open sourced it, right? Then, and it was about 2019, I think it was before COVID. So this is so the next one we do, and it uses MLIR now as an established way to.
There we go. Yeah.
Right, the unit felt different backends. So I think we see real progress here.
Oh yeah, definitely. I mean, at least MLIR is pretty daunting though when you start because it's loosely coupled. Mm-hmm. So dialects, they compete, they rise, they fall. So it's hard to essentially do your way into it. This was also, dialects. It may seem, it is a very like semantic is how you get performance, is how you get true agnosticity. So, there may come another dialect, the ones that essentially is better than them all. But for now, this one is pretty cool. Stabilicello, it's called. It's pretty cool because everybody sprouts from it too. So all vendors essentially take this as input and then will run their own dialects. Sometimes in closed source, TPU is one example. It's completely closed source. There's no it's literally a shared like an SO file you download, and you do it all.
I was wondering about the language thing because it's the big bet, right? And as you know, in a completely different space, I'm working on a product that also has to convince people to write new code on a new set of APIs, and language choice was a big issue. I'm wondering, just in case you run into objections to adopting ZML because of Zig, do you have tools in the toolbox to address that? Like, I don't know, can realistically the smartest models port my PyTorch codes to ZML? Could you in the future have some sort of a multi-language binding situation? I know right now, the bet is that you won't need it, but just in case. Well, especially the porting, the transpiling. Is it realistic? So I want to try it. I want to play with it. And maybe I'm not the target audience because I'm not an expert productizing a model, but I like the idea that, okay, I can express this code, as I can experiment, especially the multi-model use cases you showed, like, I could do like a cool video related or sound related model. Maybe start with an expert's model and then play around. That's appealing, but at least because I don't know Zig, it's not that I don't want to learn it. Right. It's just that it's one more thing to learn.
Absolutely.
Anyway, I'm just curious about that topic in general.
That is a great question, and on after which there are actually multiple answers, because there's lots of actually all valid different answers depending on where you sit. So a lot of people, they just want to run let's say a Llama. So they don't care about how it's written. They just want a server. They want to run it, and for them, we have that ease of use that you just saw. Then we have the people who want to run custom models, right? Custom Llama models, right? Fine-tuned or whatever, Mistral and so on. They're based on Llama architecture. Again, these ones don't need to touch anything with Zig. Then there are the people who have their custom models, but lots of these models are essentially assemblies of primitives, transformers, and so on. So for them, there's not a lot of code to write in Zig, right? And then you have the hardcore people who have their very custom thing, who actually, have to write the whole model code in Zig. So not assemble parts, but actually, like a transformer layer, but actually do the, really deep down operations. There are a few observations we made along the way. When we built the framework, the first one that, we actually did build the framework by porting models over to ZML from PyTorch, right? What we found, we actually used to have a leaderboard about it, is that 80% of the time, and I will answer, also the perception of things, right? But, in fact, 80% of the time was spent trying to understand what the hell, was written in PyTorch code. And this is probably, less than what it really was. So that was the first thing. And the second thing, which came as a surprise, sort of, was that since the launch, the Zig situation, so to speak, has been a complete non-issue. So I have a few explanations. I don't know why that is. I have a few explanations. I think one of them is that they were trying to jump the boat onto some new technology, and Rust was maybe a bit too involving. So maybe they were waiting for an excuse to diving into Zig, but I had so many people just reaching out to me and say, I guess we're doing Zig now. And I'm like, okay. But So this is like, what's happened. And also, yes, we have tools to ease that, essentially, that porting. We haven't released them yet. There's a few reasons for that. The first one being that we didn't want essentially to cater to everybody. We wanted to cater to the people who would essentially involve themselves. But also, it's very easy to fall into a long tail situation. And this is a story we see over and over again, at least in PyTorch, is that it's very hard to get that I would say, that level of ease of use, like very multi-year effort to get that ease of use, because the abstractions don't play well by essentially doing, let's say, code transformation or like tracing. So what a lot of people do is tracing. So Apple does this with CoreML, transformers. A few people that do that to try and PyTorch XLA does that too. The problem is that you end up with a lot of essentially generated code, which is exactly the PyTorch code, mind you, right? But it's not less clear. It's not much clearer. So it works as a gateway, but what I'm trying to optimize for, I would say in the midterm, is so that we do the 95%, and we strike that balance between saying, hey, PyTorch is not the front end of ZML. There's an import that happens. We do the messy stuff, and then you can do the nice stuff of the polishing. But ultimately, yeah, we have found to be.
I have a follow-up question, but
sure,
I don't
go ahead.
hog the mic. Okay. Go ahead.
So Steve, I have an intuition, and I wonder what you think about this. So, so we started this AI Alliance, which is open source coalition of IBM, Meta, and 100 other companies, and there is a very vibrant community there for industrial AI, right? Which is very different from Silicon Valley, almost unheard of here, like because we only do Uber for pets here, right? Like we do this kind of stuff. Like in industrial AI, people embed AI in machines, right? In turbines and factories and stuff. Right. So instead of LLMs, they're thinking about something called SSAs, small specialized agents. So this is going to be custom, models trained on the domain and embedded in machines. And to me, basically, like you did in C, in C++, and Zig is a successor of this with a modern stack. So would this stack be useful for this kind of applications which are not connected to the internet, locally all hosted, right, in machines?
Yes. So we talk to, not industrial, but we talk to people who have similar, I would say, requirements. There's a huge, I would say, blind spot, in the AI market, or at least in the AI discourse, which are latency-bound workloads. These are we found it to be like a very, very big, portion of the market that nobody talks about. So it's not about LLMs also, it's like transformers, etc., but bound by latencies, right? So fraud detection, that sort of stuff. So we're a good fit for these, use cases, industrial too. The reason being that we have essentially, it's not so much that we have low latency, it's that we have predictable latency. So it doesn't go all over the place, right? So for I would say mission critical, fraud detection being, a big use case, ad routing and so on. Because, there's a compiling step and an execution step, there's much less variation in latency. And the second, maybe technical answer to that is why also we went with, a language such as Zig, or it could have been C++ or Rust, is that we could integrate it completely into something else. It's not always a serving situation. It could be integrated into something. As long as you have an accelerator, you want that. We don't do ahead of time compilation. We could, but it's a very big mess at the moment, and there's no real value because you'd rather have one deployable artifact that essentially will use whatever is available dynamically to the full extent. Could be the CPU, let's say instruction set, if you run on CPU. So that way we haven't pushed the ahead of time, and I would say small, deployments, mobile and so on. But for industrial, of course, like if you have a CPU, if you have an accelerator, yes, absolutely.
Can you maybe elaborate a little bit on the Can you maybe elaborate a little bit on the predictability? Why is it more predictable? I'm not sure I understand.
So there's a few reasons for that, but I guess the bigger one is because when the model runs, only this happens. There's no caching. So there's no hidden, I would say, compute that goes on. When you execute a call, we talk to the GPU, we execute a precompiled, kernel, well, program, so to speak, and it's the complete, forward pass that is encoded into that program. So as long as would say, and mind you, because the shapes are static by design, you can actually predict how long it's going to take on the more or less through OS viability and so on. But like if you take for instance JAX or PyTorch, in the case of PyTorch, it's fully dynamic. So you don't know, right? If somebody adds changes whatever input, then you run a bigger kernel, right? It's fully dynamic. In JAX or PyTorch XLA, there's hidden compilation that goes behind the scenes to try and essentially give you that dynamism, which actually doesn't exist at all because it doesn't even exist in the model itself. Models are trained with static shapes. So batches can be dynamic, but you want to push that a layer above. You want to be able to route to whichever, I would say, version of the model you see fit. So this is why we have predictable latency and flat too. Now, this is on the model side, but then also there's the rest, ingesting the bytes, normalizing the bytes. And for that, this is where Zig shines, especially through its allocators pattern. Because we can choose, each allocator we want to use on the journey to that. And it's not like we can make that essentially very predictable, especially through arena allocators. Come again?
Because you control.
Yeah. But the idea is just, it's not to add complexity. This is to me the important part. It's just to ask the good questions at the time where it's cheaper, where it's the cheapest to answer. So allocators are a good example. If you're going to run an operation that will allocate memory, which creates uncertainty, a certainty in execution time, then it's better to ask me when I'm about to do it to write that code, than me trying to trace everything and finding that it was this endpoint that was essentially exploding in latency. So by asking the question at the moment in which you write the code, in this case, which allocator would you like to use? You can use the default allocator. You're good. It's like the same thing you would get with C++, whatever. Or you can, since you're asking, well, yeah, maybe I can go a bit fancy. And this is actually, you squeeze a lot more performance out of everything. And it's very, subtle. But first of all, it adds up in ways that, you don't, I wouldn't have thought. But also, it feels very nice because you're in control and there's like much less surprises, especially in a production environment.
That's actually a great segue to my part 2 question, because it's about embedding. Well, you're explaining why ZML is great for embedding, basically.
Yeah.
It miniaturizes the implementation of the model, I guess. There's no hidden runtime and all of that stuff, so it's perfect for embedding in an industrial platform. Connecting that to the language question, I'm wondering if that also makes it perfect for embedding in any software product, right?
Yeah.
Like, could you wrap your ZML model? Like, talking about the layers of use, right? Maybe I want to modify or customize the model itself, then it's Zig, because I'm interacting with the ZML API itself. But if the model is great, I like it as it is, can I pop up one layer, and could you give me, or could a third party in the ZML ecosystem package any ZML model as a Go library or as a Python package?
So,
and I just import that into my application, I embed it, and I'm not using the ZML bindings,
Sure.
I'm just using that model, and it has its own API, and I would use that probably until the moment where I think, oh, I would love to customize that model.
Yeah. So
and would it be real? Like, could I mix and match several models that way, or would it be so slow to do the round trips that it would just not be worth it?
No, because there are round trips, but models are big, so it amortizes. But I will let you guys in on a secret. This demo we did was exactly what you described. It was a Go server with ZML as a library. So for those who don't know, the demo is like we got a Llama running, a small Llama model running, with a few layers on an AMD GPU, few layers on a NVIDIA GPU, few layers on a Google TPU, and all of that over internet. Shard, yeah, pipeline shard.
And which model is it?
Llama.
So it's like Go Llama?
It's like what?
Go Llama?
Yeah, sort of.
Llama as a Go library? I would use that.
But
I'm probably not smart enough to use ZML, but I'm smart enough to use Go Llama.
No, so the reason we didn't push for it is that essentially the FFI you need to write is very dependent on what you want to do. There's like lots of answers on the journey. So mind you, Zig has perfect C integration, in and out. So by far the best I've seen. Like it's close to, if not transparent. So it's very easy to make a C API. Also, if you use Bazel on top, it's like literally zero. The integration is literally, there's no downside to it, except for the FFI layer, which is unclear exactly how you would want that API to look like. The reason being that on the Zig side, there's a lot of sugar we implement to make that easier. So like when you do the compiling, for instance, we would spawn that into a background thread so that you can do other things while the model is compiling. So for that, so it's embeddable, right, mind you. But we have an asynchronous runtime that we can bind to some other reactor. If you run into Tokyo, then we can hook into Tokyo and use that. Sorry?
What's Tokyo?
Tokyo is the Rust asynchronous runtime, or the Go, for that matter, runtime too, because you don't want to have 3 reactors in your process communicating over thread. It works, but it's suboptimal. This is why we have this, little thing here, async.zig, which is, stackful asynchronous implementation, so that we can have, essentially stackful coroutines, Go-like, on top of Zig, right? So this is how we do async compile, then do some other things, then wait on that, and so on. So the reason we haven't pushed for the, let's say, the FFI libraries is that during that demo, we found that it was very dependent on what you were after. And it was more like, it was very much bound to the user code as opposed to ZML code.
Can you explain that in another way?
So for instance, you might want to say, hey, you know what? I have 2 methods. One is prepare, let's say, and the other one is run, right? And run takes a slice of bytes or floats, and then it, so it's very high level at this point, right? But sometimes, you want to have lower abstractions. For instance, if you're in the demo, we shard the model into multiple places. So what we compile is not the whole forward pass. It's only the transformer pass, right? So instead of having, 1 execution per token, we have, 40 executions per token. Because at each time, the layers have done, then we take the data, we send it over the internet, put it back, and re-inject it. So you have varying levels, essentially, of FFI code you want to write. So, and because it wasn't clear, essentially, we could do an API, but it wouldn't feel really, it wouldn't feel something, I wouldn't say usable, but we haven't found yet, when is the balance between, or like to put out an API.
And just to make sure I understand, like to do it correctly, so that I can really fully take advantage of it. Say in my Go program, there would be some Go specific work you would have to do. Like you would be basically writing a thin Go framework on top of ZML, but then you have to do that.
We could. We wouldn't need to, because if you put that abstraction, very high, then the C code is just taking arrays of floats, and that's it, right? Maybe a shape, and that's it. So it's very static. But if you as you go down, then you start to want a bit more infrastructure or sugar, right? So in the case of that demo, we had quite a bit of sugar, and FFI and bidirectional. And the issue with FFI is that if you haven't done it before, it's very easy to shoot yourself in the foot with respect to ownership of data, between languages and so on. So it works, mind you. But we want to do it like we wouldn't just want to strike the balance if we go multi-language. But in the meantime, we found that people would just say, all right, we'll just do Zig now.
I'm sorry. For me, FFI is foreign function interface.
Yeah.
How does that?
CGO.
Yeah, CGO. So how is that in your 4-windowed demo? Where does the FFI get into play?
Oh, so
because those were 4 machines, right?
Yeah, but they were running a gRPC server written in Go.
Okay.
So the Go server was calling into ZML.
Go.
Come again?
The FFI was
Go.
Yeah. Okay.
Yeah. But there was also a Zig part, which is to expose the Zig API as a C API. So that part was, the reason we found was that API that we would expose, it was really bound to how we would use it ultimately. So because we were not really sure how to entangle that thing, because it was really depending on the use case, we tried to be generalist about it, right? This is why we pulled back a bit, because we found that there would be a balance we would find, and we would have to search, then find, that just, that was self-evident to everybody.
Okay, so basically you're saying that the FFI API you came up with for the demo was a very, unstable API, and
yeah, I mean, it worked for that demo.
Okay.
Right. Yes, exactly. Come again? Oh, Swig as in, the C++ to whatever? I'm not aware of it, but I think, so I used to be a pretty big user of Swig. I have a few patch. It takes C++ code and it generates FFI code in Go, in a few languages, but I use it most notably in Go. I would go on a limb and say that, so you mean like to generate Swig code from C++ code?
Yeah, so you're writing a Swig interface file
yeah.
to generate basically a C or C++.
Ah, right, yeah.
For Go, Python, or Java.
So there wouldn't be any point in doing that, because Zig's C story is actually, state of the art. Actually, is way higher than everything else. So it's actually easier to just create the API in Zig that is C compatible than just having being generated.
Well, you're actually generating an API
for C.
For Go callers.
Yeah. I mean, we could, yeah. I mean, we could.
Swig would be generated.
Yeah, but you might want to have over that Swig code. I used to use libtorrent that way, which is a C++ library. I would have Go code on top of it. So you have, so it simplifies the CGO situation, but there's a cost. There's a lot of heap allocations involved also, and the setters and the getters and the whatever for C++. I would say that it wouldn't be really needed, because ultimately the value add wouldn't be amazing because it's a C interface. It's very valuable when you, at least for me, it used to be very valuable for C++ when I would instantiate templates and getters and setters and operators and so on. But in the Swig interface, but in that case, technically you could have Zig emit a header, and then give that header to Swig and it would work, right? Yes. But we found it to be, it could work, but ultimately for that demo, we just had a header which we see imported in include C in Go, and it worked fine. And then we added our sugar on top of it. It turned out that our sugar was very dependent on our use case, which is why we pulled back from pushing forward on the FFI side.
Since you're basing everything off XLA with NVIDIA and AMD and Google TPUs, have you considered AWS's Neuron hardware inference and training?
Yeah, we're working on that.
It's actively under development. Okay. Do you have any timeline associated?
Let's talk after.
Well, if not, then one more.
You know that my friends, right? They're supporting me.
Still, I just wanted to say what's next for the project, and that'd be a
Yeah.
good way to end.
Oh yeah. So we're working on the LLM server, obviously. The serving side, more chips. An active area we're working on is sharding too. So there's code was merged. I think it was last week to do sharding. So essentially, split a model across multiple GPUs. I would say the opinionated thing we have is that we think that you wouldn't want to use machine interconnect in pod. So our base assumption is that you have a fast interconnect inside the machine. So you're running tensor parallelism inside the machine, so sharding, etc. And slow, or let's just say not InfiniBand, interconnect between machines. So if you're going between machines, then you might want to run pipeline parallelism. So just get the activations, transfer them, re-inject them. This is the demo you see. So sharding, is the one that is top on the list because this is how you run the 7TBs and stuff. But it's easier said than done to do it in a way that is performant by avoiding copies over and over again. Because when you run the operations sharded on multiple GPUs, there's a lot of crosstalk. And there's some tricks people use to essentially make it look like it works, but it's not rainbows.
I actually thought of a question. So we have TED.ai coming to town, which is October 23rd, and I happen to be a judge of the hackathon. The hackathon is on 19th of October, so Intel sponsors it, and it's a big deal with a lot of people. So let's say I want to suggest to some folks to do a project in ZML, right? What are the resources they can take to do this, one kind of cool demos people do with voice and video, whatever, using Llama and stuff?
So the first thing they might want to do is go to the documentation website, if Chrome is opening. So this is how you get started. So we essentially take you from zero to a working, I would say, matrix multiplication on a, so like you have how to run Llama, etc. But also we have examples such as that one. That one is a basic matrix multiplication benchmark that tells you how many flops ran, right? So this is a great way to get started to see essentially, because these models, like examples, they essentially show you the framework. They don't show you models. They show you, this is the model. It's a dot product. This is the framework, right? Parsing of the flags, the compiling, and et cetera, et cetera. So the best way to get started essentially is to take that examples folder, copy it, somewhere else, remove models you don't want, and just get hacked, hacking, right?
And let's say you want to use the community to help you build out ZML. What are the low-hanging fruit things people can do to contribute?
Models are cool. Diffusion, we have somewhat on enough effort of, so we used to have about 8 models total. As we were working on the framework, we stopped working on them to concentrate on polishing. So we just wanted to have Llama running at all times and then NIST, So there's an effort sometimes that Guillaume of our team is live streams on porting over stable diffusion. But stable diffusion, multimedia models. We actually used to have a demo of an AI audio codec running inside of FFmpeg through ZML in the same binary. So I guess more models existing models, whatever. And if they see some things they don't like, please tell us in the API. There are varying levels of abstraction in the framework between, the basic tensor operations to NN, to, IO, to that sort of stuff. We have a very opinionated also IO model too. So,
All right. If there is no more questions, let's thank.
Thank you, guys.